Let's say we have a mass hanging from a spring. We also know that gravity is acting on that object. Then by Newton's third law, there is a force opposite to that one. We say that that force is proportional to the distance that the mass has displaced. However, the sign change because of the force is in opposite direction. We should add another constant to our equation related to the stiffness of the spring. We call the key the greater K, the greater the stiffness, then the more force we have to apply. Then we begin our analysis for the sake of the analysis. We say that K over m is equal to 1. Then our equation becomes acceleration equals minus x. Though we are trying to find a solution for that differential equation, we are going to do by numerical analysis. Suppose that at a given time, t, the object has a certain velocity, vx, and position x. What is the velocity and what is the position at a slightly later time, t, plus epsilon? If we can answer this question, our problem is solved, for then we can start with the given condition and compute how it changes for the first instant, the next instant, the next instant, and so on. Our initial condition is that x is equal to 1, the time is equal to 0, the acceleration is equal to minus x, and the velocity is equal to 0. So we have three equations. The first one tells us how x behaves in a small time t plus epsilon. We have x at time t. We add epsilon times velocity, which is the distance at a small time epsilon. The second equation tells us how v behaves after some small time epsilon. First, we have the velocity at time t, and we add epsilon times acceleration, which is the velocity at some tiny time epsilon. The last equation comes from our equation of the mass hanging from the spring, that the acceleration equal to minus x. If we find the distance, velocity, and acceleration at some time epsilon, we can use that data to iterate in order to find the next distance, velocity, and acceleration. Here is a table that shows the results. We see from the results that x equal cos of theta is a good approximation to the acceleration. Then we compare our two equations. One says that the acceleration is equal to minus key over m times x. From our last analysis, we see that x is cosine of t. However, if we see our first equation, we have to account for the constant k over m. So x cosine of t becomes x cos omega 0 times t. We would call omega 0 the angular frequency. Now, if we differentiate twice x, we would get an equivalent equation as our first one. So the second derivative of x is minus omega 0 squared times cosine omega 0 times t. We see that our constant k over m is equal to omega 0 squared. Hence, omega 0 is the square root of k over m. We know that the period of oscillation is 2 pi divided by the angular frequency. Then the period of oscillations is 2 pi times the square root of m over